Thanks for the intro. So my name is Albert Kwon, and I'll be talking to you on our work on Riffle, an efficient anonymous communication system. And this is joint work between myself, David, and Srini at MIT, and Brian at EPFL. So let's say Alice and Bob wants to talk to each other, and in particular, let's say Alice wants to send some confidential document or a video to Bob. So our goal is to allow them to do this anonymously. I'm sure everybody here at least agrees that anonymity is generally a good thing. So, what can we do? So there are two forms of anonymity in particular we want to provide. The first is sender anonymity, where Alice's identity is protected from the rest of the internet and Bob. So this is particularly useful if Alice is a journalist or a source, and she doesn't want that, the document or that information associated directly with her. The other form of anonymity is receiver anonymity, where Bob's identity is protected from Alice and the rest of the internet. So this is useful, for instance, if Bob is WikiLeaks and he doesn't want his true identity known to avoid, persecution or shutdown of kinds. So these are the two forms of anonymity that we would want. How can we do this right now? So really the state-of-the-art way to do this would be to use Tor, and in particular use Tor hidden services to get both forms of anonymity. Unfortunately, in the past decade or so, we've seen a lot of different attacks on Tor, and some of which are in particular to hidden services. And in general, Tor's weakness against global adversaries and traffic analysis attacks weren't something that I wanted to see in a very strong anonymous communication network. So we wanted to design something better. So before we get into our protocol, we can first start with mixed nets proposed by David Chom in the 70s and 80s. So we go even farther back than Tor was proposed. The high-level picture of how mixed nets work is kind of similar to Tor. You have a handful of servers, and the messages are routed through these servers. But instead of routing one message at a time, directly as they come, instead you gather a few users' messages, usually actually many users' messages, and each user submits an onion encrypted message for all the servers, right? And each server takes in these messages, decrypts a layer, randomly shuffles them or permutes them, however you want to call it. And second server does the same, and the last server is in charge of relaying the messages to its final destination. Right? And this is how you get sender anonymity, because if these shuffles are random, you shouldn't be able to associate which message originated from which client. So there are two problems with with mixed nets. The first is that, at least by default, there's no receiver anonymity. So here, as you can see, the Alices on the left needed to know which, the Bob's identities and indicate to the third server that, this message is meant for, the red Bob, for instance, right? So there's no receiver anonymity. And the second is a little more subtle, in that if you start having actively malicious servers who are permuting your messages, then you may not even have sender anonymity. So consider this example attack where the first server and the last server, say, are malicious. So when these messages come in, the first server is going to replace all messages except for one that is interested in de-anonymizing. So in this case, the red message here, sent by the last Alice on the left. So the other messages are, onion encrypted garbage messages, essentially. And the second server has no way to really tell that this has happened because everything here is using public key crypto. And so it's going to happily carry out this protocol, and the third server is going to, just drop all the garbage messages and then just relay the red message only. So now the adversary knows that the bottommost person on the left is talking to the red person on the right. So in general, these sort of tampering attacks, where the actively malicious mixes or the servers tamper with your messages, is the reason why sender anonymity may be broken in practice in mixed nets. So how can we fix this? So in 2000s, there was a new crypto primitive called verifiable shuffle proposed to exactly address this problem. So here, what happens is when a server shuffles or permutes these messages, it also generates a zero-knowledge proof of the permutation. What this means is that it's a proof that the output forms a valid permutation of the input. So you can tell that no message has been tampered with. But it's also zero knowledge with respect to the permutation in that nobody else actually checking this proof can tell whether, what permutation or how it was actually shuffled. So this is how you keep the security of the shuffling and the random permutation without, while preserving this tamper-proof property. And so, if the second server misbehaves, now the first server misbehaves, then the second server could check the proof and whistleblow with, the zero knowledge proof and the messages it got, and let everybody know first server is misbehaving. Okay. So with this in mind, we can actually create a verifiable mixnet where you use verifiable shuffle all the way, and this actually you can show that this preserves sender anonymity even in the actively malicious cases. And we kind of add a kind of trivial form of receiver anonymity by broadcasting, say, all messages to every recipient in the network, every potential recipient. So again, so this kind of trivially achieves receiver anonymity because all messages that are sent to everybody, you don't know which message is meant for whom. So the two main, so this actually satisfies the security properties that we want. It provides both forms of anonymity, but you have two big problems with performance. The first is that verifiable shuffles are very computationally expensive. So to give you a concrete point, it takes a couple of minutes to shuffle 100,000 short ciphertexts, think symmetric keys, like 128-bit symmetric keys. So if it takes a couple of minutes to do that, we can't really use this for any sort of latency-sensitive communication. And the other one is fairly obvious. You're broadcasting the whole message. You had this O to N bandwidth overhead per message. You really don't want this. And to make this worse, this is between every client and server rather than, say, server to server. So because of mixed nets, you have, say, a handful of servers. Maybe you can assume they have good connectivity between the servers. But it's really hard to do that, or really hard to assume this between every client-server pair. So Riffle protocol aims to solve these two problems exactly without sacrificing the security of the scheme I proposed before. So before we move on, the security, the model in which Riffle is used is similar to mixed nets. So we have a handful of servers that collectively behave as an anonymity provider, and we have lots of clients who wish to communicate anonymously. And we allow all but one server to be malicious, and the identity of the honest server need not be known. We just need guaranteed existence of one. And also, we allow any number of clients to be malicious, and our goal is to provide anonymity among all the honest clients. One last thing to note is that communication in Riffle is done in rounds to avoid traffic analysis resistance. So in every round, every client uploads or sends and receives a message, so that it can't get singled out by not uploading or not downloading something. So first thing we address is the computational overhead of the shuffling. So the high-level idea is actually quite simple. What we're going to do is we're going to use verifiable shuffle to set up symmetric keys. These keys are pairwise for every client-server pair. And then we're going to then use authenticated encryption and just use symmetric crypto to send the actual large messages. Right? And so to say it another way, we're bootstrapping verifiability of the expensive crypto by using expensive crypto ones for the symmetric crypto. And we'll see the details. So hybrid shuffle in detail consists of two phases. The first is setup, where the actual keys are shared. So each client generates a pairwise key for all the servers, and it's going to onion encrypt a different number of layers depending on which server it's meant for. So for instance, if it's meant for a first server, it's going to do onion encrypt it once, second server twice, third server 3 times. And so once these keys are collected at the first server is going to decrypt the layer, and it's going to keep the keys meant for it, and it's going to verifiably shuffle the other keys before sending it to the second server. And for both sets of keys, it's going to use the same permutation. Right? The second server now does the same, and verifiably shuffles the keys for last server and does the same. So at the end of setup, all the servers now have some permuted version of the keys. And because these keys are verifiably shuffled, they have guarantee that these keys originated from the clients. And it's also the zero knowledgeness of the verifiable shuffle guarantees. They can't figure out which client sent which of these keys, at least for the honest clients. So once the keys are set up, now to upload, you're just, so this is when they actually send the messages, each client just simply onion encrypts their message with the keys they shared earlier. So first server is going to kind of trivially match these keys, decrypt the layer, and it's going to permute using the same permutation as it did with the keys to permute these one less layer ciphertext. And now when the second server receives them, because it's the same permutation was used, the keys and the ciphertext naturally line up with each other. Right? So without knowing the actual permutation or who sent which message, the second server can decrypt the layer. And again, do the same for the last server, and the last server can finally output a permuted version of the plaintext messages here. So now, so it's a zero knowledge. The zero knowledge property ensures that none of the servers learn the actual permutation of the ciphertext messages, and also the fact that we're using authenticated encryption means that first server can't really tamper with the messages for the downstream servers, because the second server, for instance, would catch this, right? Because the first server doesn't have the keys, the necessary keys to tamper with it. And authenticated encryption guarantees the CIA of the symmetric crypto. So that's the ciphertext. And so upload can be done over and over again, and this is how we amortize the cost of extensive public key verifiable shuffle. So to improve the broadcast bandwidth, we use PIR. And so we replace broadcast with simply just multi-server PIR. I don't have details to go through the scheme or our optimizations, but if you have M servers and N clients, what we get is that between client and server, we reduce N messages to just one message plus N bits. So even for a million clients, it's just a million bits. It's actually just one bit. And we believe it's fairly reasonable. And but this doesn't come for free, as we introduced a new metric. So we have to send M minus one messages between servers. But two things to note. One, the total amount of bandwidth is still much less than N messages. And two, we believe the server-to-server bandwidth in practice will be cheaper than client-server bandwidth. So there will be some savings in practice also. So we've implemented a prototype of this in Go, and we've tested on the Emulate testbed. For majority of our tests, we had 3 servers and varying number of clients evenly distributed among all the servers. And the clients were connected to the server using one shared 100 megabit connection, and the clients, or rather the servers, were connected to each other using 1 gigabit connection. And we tested it on 2 different applications. The first is file sharing, in which every user uploads a large file and downloads a large file through PIR. So the dotted line here shows what we call an ideal version of the Riffle. So this is what would happen if we only had bandwidth to consider. So how long does it take to literally move this many bits? And this takes into consideration both client server bandwidth and server bandwidth. So the solid line shows our prototype implementation. And the fact that the gap is fairly small, I think seems to indicate that the computational overhead of both hybrid shuffle and PIR is fairly small for our scheme. And also, in terms of concrete numbers, we can support about 200 to 300 clients at 100 kilobytes per second. But as we mentioned before, this is heavily bandwidth limited. And in practice, I think client and server in particular would have more bandwidth. Just because you're adding more clients, you're not going to have less bandwidth available per client necessarily, especially at 200 to 300 clients. So we believe that these numbers in practice could be even higher if we had better bandwidth available. Another application we tested on was microblogging, so similar to something like Twitter, where one person would post a small message, and this is immediately broadcasted to everybody. So we assume that one person may be interested in reading a large number of messages. So here we just assume broadcast to get kind of the worst case behavior. So in this application, we were able to support about 100,000 clients with less than 10 seconds of latency, which we thought was fairly reasonable for something like Twitter. You post your message, and 10 seconds later, it appears on everybody's feed. And another thing to note is that if we double the message size, the latency essentially doubles. And the similar effect also holds if we halve the message size. So this kind of enables different trade-off space for the application designers. So depending on what size message you want, how many clients you want to support, et cetera, they can actually choose the parameters that fits their needs. So in conclusion, I presented our protocol Riffle, which combines hybrid shuffle and PIR together to get anonymous communication for both sender and receiver. And our prototype demonstrates its effectiveness in 2 different application domains. And we have our research prototype available at that GitHub link. Thanks, and I'll take any questions.